In this video, we will explore the absorption and transmission of light using color filters. When light strikes an interface, it can either reflect, transmit through, or be absorbed by the new medium. Color filters are films that allow some colors to transmit, meaning they pass through and can form an image. Meanwhile, other colors are absorbed, and as a result, they are blocked. There are color filters of different types, and we can tell which wavelengths they block by looking at a graph of irradiance versus wavelength. Irradiance is the light power per unit area. This helps tell us how much light is detected. If you look at the graphs for LED lights, you will notice that the blue LED shows a high irradiance in the blue range of wavelengths, between 440 and 500 nanometers. The green LED shows a high irradiance in the green range of wavelengths, between 500 and 560 nanometers. And the red LED shows a high irradiance in the red range of wavelengths, between 600 and 650 nanometers. The white LED shows irradiance over the whole visible range of wavelengths. We can also use percent transmission versus wavelength graphs to understand our filters. Smaller transmittance numbers mean less light is transmitted, or that more is absorbed, by the filter, while higher transmittance numbers means that more light is transmitted, or that less is absorbed. Using the graphs, predict what colors will be absorbed or transmitted. In this activity, we will use a series of 4 different colored LEDs: white, blue, green, and red. First, we must use a lens to focus the image on a screen so we can see the individual colors sharply. Here, we have a series of different filters whose graphs we saw earlier. Deep straw, which transmits and looks yellowish-orange, deep golden amber, which transmits and looks reddish-orange, and Prussian green, which transmits and looks bluish-green. For example, if we look at the deep golden amber graph, we have zero or low transmittance from 350 to 550 nanometers. This means purples, blues, greens, and some yellows will be absorbed and blocked. From 550 to 750 nanometers, we have high transmittance numbers, meaning oranges and reds will transmit and be visible. First, we place the Prussian green color filter between our LEDs and the image screen. Notice how the image changes. Some colors are transmitted while others are absorbed by the filter. This filter absorbs reds, oranges, yellows, and some purples, which blocks them in the image. Blues and greens are transmitted, and you can see them in the image. Next, we place the deep golden amber filter. This filter absorbs purples, blues, greens, and yellows while transmitting reds and oranges. Finally, we place the deep straw filter, which absorbs purples, blues, and a little bit of greens, while transmitting yellows, oranges, and other greens. Take a look at the combined LED and filter transmittance graphs. Notice that the Prussian green filter transmits greens and blues around 450 to 550 nanometers. Our red LED has a wavelength around 630 nanometers, which is outside the transmitted portion of wavelengths. This means it is absorbed and we won't see it in the image. In general, wavelengths where the LED area overlaps with filter transmission area will be transmitted. This is shown by the darkened areas. The LED areas that do not overlap will be absorbed. This is shown by areas that are undarkened. Does this make sense with your results? For the Prussian green filter with a white LED, the area of overlap consists of blues and greens. These are the only colors we should see. For the deep straw filter and green LED, green is the only color we should see because those wavelengths are the only areas where we see overlap. For a deep straw filter and white LED, only green, yellow, and a little bit of red overlaps. We should see mostly green and yellow with a little bit of red.